Okay, well, a little bit more time on the basics, and then we'll show some examples of Fourier transforms. We'll look at the discrete Fourier transform. And just as a refresher, remember that the Fourier transform is this idea is that we can take any function, f of t, you name it. It could be stock market fluctuations. It could be, the number of cars passing a certain point in a certain time interval, and just about anything. It could be the topography. You might want to represent that as a Fourier transform. So, as you remember, the challenge for us was to find these coefficients, the a sub n's, the b sub n's, and so on. And the way we did that was we used the sine and the cosine as filters to, in this case, filter out the ith term. And this is actually going to be the only non-zero integral because we have the cosine squared of I omega t. That's all positive. So it's going to have a positive area. And so the relationships that we came up with were in order to get the first constant that turned out, and we're expressing it in a radian form here. We just take the integral of the function over time. And that you would imagine is just going to give you the average, and it does. We refer to that as the zero frequency component. Then we get the coefficients for the cosine terms, the coefficients for the sine terms. And again, the cosines and the sines act like a sieve. They filter out one term. They filter out the nth term in this case, which gives us the value of a sub n, or with the sine, the value of b sub n. So we can get all these coefficients. It seems rather laborious. There are elegant techniques for doing this that we won't get into, but that's kind of the basic idea. And here we're going to just note that if you continue your studies, you're going to run into expressions in exponential form, and the cosine turns out to be the real part of e to the n omega t, and the sine turns out to be the imaginary part. So you'll often see this kind of an abbreviated notation for cosine and sine. So we know that the Fourier transform takes this signal, whatever it happens to be, whatever it is that you're interested in. It you have this function in time, let's say, and it converts it to an equivalent function in frequency. And vice versa, though. We have what's referred to as a forward transform. We're going from time to frequency. And here we have an inverse Fourier transform, which takes us from frequency back into time. And you'll often hear, as noted here, you'll often hear people talk about time domain, frequency domain. These functions are in time. They're referred to as the time domain. The Fourier transform gives you a function which is in the frequency domain, this function here. So we'll also, most of the data that you're going to be working with are not going to be continuous functions that you can describe analytically. They're going to be digital. You'll be looking at, some process, and you'll be sampling it at a constant time interval, and whatever kind of data it happens to be. And so the functions that we happen to be looking at look more like this than the ones that we have over here. So this will be the discrete Fourier transform. It takes a function sampled in time, transforms it into frequency. Here we have the inverse Fourier transform. Takes the function in frequency and gives you back a function in time. So we're going to just take a quick look at some examples. We'll try and come back to some more examples and give you some, to show you how the data can be analyzed. But if we take the Fourier transform of a sunspot cycle sequence, which comes up through about 2010 here from 1945 to 2010, well, you've probably all heard that there's an 11-year sunspot cycle. And we can see here, this is the Fourier transform. This is the discrete Fourier transform. This is the frequency domain representation of this time series. And you can see that there are hints of other cycles. We have an 11-year cycle here, or close to 11 years. There's also an 8.1 year and a 32.4 year. Very low amplitude, hidden in the noise here probably, but it does show up. And so if you're thinking about physical processes on the sun, you're probably thinking, well, now what's going on at 8.1 and 32.4 years? We were pretty familiar with this one, but these are additional insights that we gain by taking the Fourier transform of this time series. Now, reflection seismic data is just another example of a time series. So we've got here a series of traces that are sampled in time. This is going from about 0.8 seconds down to 1.3 seconds. This is out in Wyoming. This is Teapot Dome. If you Google that, you'll find some interesting historical information. But the Fourier transform of this data set is kind of, you can see that the seismic frequencies are kind of localized between around 10 hertz to 60, maybe 70 hertz. There's some additional signal out here up to about 90 hertz, and then we're kind of into the background noise. So two examples of discrete Fourier transforms and amplitude spectra. So this would be referred to as an amplitude spectrum. It shows the peaks. This is probably easier to relate to. We've got lots of different frequency components here, no individual component really standing out. So what I wanted to do was kind of refer you to this very useful website, www.falstad.com, and we'll take a look at this, and we'll bring up sines, cosines, sawtooth functions, squares, triangles, noise, and so on, and take a look at their behavior. Now I'm going to turn on the sound here, and you can hear this sine wave. It's about 222 hertz. If I roll this down, I get it down to around 100. So that's a sine, and you can see it's kind of our 0 point for the sine would be here, going positive and then negative and positive. So if we take a look at the cosine, we start off at 1 and go to 0 and then -1, +1, -1. Sound didn't change. Cosine, sine, no change there. Now I'm going to have to reduce we talked about the Fourier transform, remember, it was a sum of the odd components of the odd arguments of the sine, and that's what you get there. Let me turn that down a little bit. Hopefully you can still hear it, but you can see these amplitudes here, 1.27. Remember, the next amplitude would be 1/3 of that, 0.424. The next one, 0.25, about 1/5. And that's the sine 5 omega t, or sine 5x, sine 3x, sine of x. Okay, well, that's a little jarring this early in the morning. But you can, and I'd recommend that you get in here and play around. There are different things that you can simulate using this algorithm here, and one of which is noise. And you can change the number of terms. You can also change the frequency, and so on. So I'd say, get in there and have some fun with this. We're also going to look at another one. It's let me change this to a filtering. We're going to talk more about filters down the road here, but let's turn the sound on. Now here we just have a noise, just kind of random noise, and it's being filtered by this function here. So the noise, which could be, goes all the way out to infinity, there's noise in the signal which is at higher frequency. But we're using this filter here. We're filtering out everything, pretty much everything above this particular frequency, which is 16,948, which is, I can't hear frequencies. I don't know about you, but I can't. So where do I start to hear things? And you can bring this, I'm not doing too good. Well, I'm starting to hear a little bit of difference there. So I'm chiming in around 4,000 to 5,000 hertz on the noise. And, well, that's not a very interesting signal. Let's try a piano. Let's bring the cutoff frequency way up here. Let me turn this up a little bit. Just going down, up the scales. And so we can hear with fairly good fidelity. We can see that there's some high frequency, as we get to the higher keys. And we can also play around with some of these, with the order and the cutoff frequency. But let's pull this down to the really low part. Okay. So we can't hear. We actually couldn't hear the higher keys there. Now I'm going to do something else. I'm going to use a bandpass filter. You notice that we don't have anything. We don't hear anything now. We can see the signal. But let's move the center frequency down. Now you can see I'm beginning to pick up the higher keys. As I move the filter down, it's picking up more and more of the higher frequency. I can change the sharpness of the drop-off here, the cutoff. Pull the and now I'm beginning to cut out some of those high frequencies. I can hear the lower frequencies, but not the higher frequencies so well. So this is something that I'd recommend that you get, have some fun with all this. The mathematics is a bit overwhelming at times. I mean, it's new, so it's the first time you've seen it, but hopefully it's exciting and interesting. And visit these two websites here. Falstead, he's got a lot of other interesting stuff on there, aside from Fourier transforms and digital filters. So that's something I'd recommend that you take some time, have some fun, looking at these relationships between frequency and time and frequency, and these filters here, because next time we are going to come back and we're going to talk a little bit about filtering. We'll come back and revisit Falsted's site, but we'll also provide some examples. So we'll use Milankovitch cycles, log data, some other seismic data. We'll play around a little bit. So we'll see you next time. Thanks for joining us.